Halberger. Today, in this series on a new way of thinking about hyperbolic geometry, we're going to look at some theorems that follow from our notion of perpendicularity, which is purely dependent on a notion of duality, which is stated very simply in terms of our coordinates. So let's begin by reviewing our basic algebraic framework. For us, a point is a proportion of three rational numbers enclosed in square brackets. And by proportion, we just mean that we are allowed to scale all of those three numbers by a non-zero multiple, and it stays the same. The three numbers can be anything they want, but they can't all be zero. A line is similarly a proportion enclosed in round brackets. And we say that the point A lies on the line, or equivalently, the line L passes through the point A, precisely when L times x plus m times y minus n times z equals 0. Now, a viewer made the good suggestion that we should perhaps also introduce a more symmetrical notation for this correspondence between points and lines. And so let's say that we'll also say that in this case the point A is incident with the line L, or symmetrically that the line L is incident with the point A. That's in fact standard terminology in geometry, and it's very appropriate for us to use that here in addition to this usage here. Okay, so given a point A, then its dual is the line x, y, z, just obtained by changing the square brackets to round brackets. And given this line L, its dual point is the point you get by switching the round brackets to the square brackets. And in terms of that duality, we defined perpendicularity both between points and between lines. So if A and B are points, we say that A is perpendicular to B precisely when A is incident with the dual of B. That's a point, that's a line. And we say that the line L is perpendicular to the line M precisely when L is incident with the dual of M, M perp. That's a line and that's a point. And we noted that this is symmetric, so that if A is perpendicular to B, then B is perpendicular to A. And similarly here. And here's the picture that we'll have in our minds. Two-dimensional representation, our base circle there, a point A, for example, there, and its dual line is given by the usual polar line of this point A with respect to this circle. There's another point B. Its dual line is this point. Its dual line is B perp right there. So in this case here, A lies on the dual of B, and similarly B lies on the dual of A. So this point and this point are perpendicular. We'll denote that by a little corner on the segment between A and B. And correspondingly, the dual of A and the dual of B are perpendicular. We denote that in the usual way, like that. And here's a little exercise that A is perpendicular to B precisely when A perp is perpendicular to B perp. And algebraically, how do we work with perpendicularity? Well, it's very simple. It just comes down to this relationship here. So, for example, the point 3, 1, 2 and the point 1, 1, 2 are perpendicular. How do we know that? Well, because this point lies on the dual of that. How do we know that? Because 3 times 1 plus 1 times 1 minus 2 times 2 is 0. So checking perpendicularity between two points, or equivalently between two lines, is simply a matter of saying this times this plus this times this minus this times this, and checking that's 0. Now let me introduce the important notion of duality for triangles. So here's a triangle, A1, A2, A3. Triangle is denoted by this notation here. And what a triangle is, officially, is just a set of three non-collinear points. So the triangle just consists of this point, and this point as a set. Now associated to that triangle is a trilateral. A trilateral is a set of three lines. And the trilateral is just the one obtained by the three lines connecting those 3 points, or joining those 3 points. And our notation is, there's the point A1, the line opposite to it, that one there, will be called, say, L1. The line opposite A2, that one there, will be called L2. And the line opposite A3, that one there, will be called L3. So L1, L2, and L3 form a trilateral, which by definition is just a set of 3 lines. And we'll say that that's the associated trilateral to the triangle A1, A2, A3. Pictorially, they're really the same. They look the same on the page, but it's nice to distinguish between a set of 3 points and a set of 3 lines. A set of 3 points is a triangle, a set of 3 lines is a trilateral. And these two are associated in an obvious way. But because of duality, there's another way of associating a trilateral to the triangle A1, A2, A3. That's called the dual trilateral. And that's just obtained by taking the 3 points A1, A2, A3 and looking at the dual lines of those 3 points. So there's the dual line of A1, let's call it capital A1. There's the dual line of A2, let's call it capital A2. And the dual line of A3 is this one here, capital A3. So those 3 lines form the dual trilateral to the triangle A1, A2, A3. And of course, those 3 lines also determine a triangle because they meet at these 3 points, L1, L2, and L3. And then it's not too hard to see that this point L1 is necessarily just the dual of the line capital L1. The point L2 is the dual of the line capital L2, and the point L3 is the dual of this line here, capital L3. So we'll say that the triangle L1, L2, L3 is the dual triangle of the original triangle. Or maybe we could say the associated dual triangle, to be precise. But we'll usually just say the dual triangle because we like to think just in terms of triangles. It's a little bit cumbersome to have to switch from triangles to trilaterals all the time. Our notation, here's a triangle A1, A2, A3. Its dual is officially the trilateral formed by the duals of the 3 points. These are the 3 lines A1, A2, A3. So the dual of this triangle is this trilateral. That's the notion of a dual triangle. So given any triangle, A1, A2, A3, there is a dual triangle L1, L2, L3. And conversely, the dual of L1, L2, L3 is the triangle A1, A2, A3. It really is a duality on the level of triangles. And one thing that the dual triangle is especially useful for is in constructing altitudes. So if we're interested in the altitudes of the triangle A1, A2, A3, it means, say, a line from A1 that's perpendicular to the opposite line L1 here. But perpendicularity is expressed in terms of the dual point. So a line that's perpendicular to capital L1 is simply one that goes through little l1. So the altitude from A1 to this opposite side is just the line joining A1 to the dual point up here, L1. So the 3 altitudes of this triangle are that one there, and that one there. Altitudes are just what we get by joining the points of a triangle to the points of the dual triangle. And we know, of course, that those 3 altitudes meet in the orthocenter of the original triangle A1, A2, A3. So let's take a triangle A1, A2, A3 and look at the structure that's created from the 3 altitudes. There's not just the orthocenter created, there's also some other additional structure which is very interesting. So here's our basic triangle A1, A2, A3 that we're going to be considering. And I'm showing you here the 3 altitudes. There's one, there's another, and there's a third, and these 3 altitudes meet at the orthocenter H. Now each of these altitudes also meets the opposite side in a point. This point here, this point here, and this point here. We're going to call these B1, B2, and B3. So it's sort of B1 is opposite A1, B2 is opposite A2, and B3 is opposite A3. These points are the bases of the altitudes. We'll sometimes just call them the base points of the triangle A1, A2, A3. And these 3 points, B1, B2, B3, form another triangle which we call the orthic triangle. There it is right there. There's the triangle there with green sides. Now that orthic triangle has lines. And those 3 lines have dual points. There, there, and there. So C1, for example, which is up here, is the dual of this line here. So it's the dual of the line B2, B3. C2 is the dual of B1, B3. And C3 is the dual of the line B1, B2. So we get a new triangle. It's essentially the dual triangle of the orthic triangle. So we'll call it the dual orthic triangle. It's the triangle C1, C2, C3. Also outlined in green here with solid green. Okay, so now here we come to the first theorem of today, which we'll call the base center theorem. And it states that in this setup, the triangles A1, A2, A3, in other words the original triangle, and this dual orthic triangle C1, C2, C3 are perspective from a point B. What does that mean? Well, it means that if you take A1, which is right here, and you join it to C1, you get that line. When you join A2 with C2, you get that line. And when you join A3 with C3, you get that line. And these 3 lines, which are dotted here in red, they meet at a point. So this is the point of perspectivity of these 2 triangles. If you had your eye here, then these 2 points would line up, these 2 points would line up, and these 2 points would line up. So I remind you that's exactly the situation that happens in Desargues' theorem. So we're saying that these 2 triangles are in fact perspective, and so there's a new point B. We're going to call that the base center of the triangle A1, A2, A3. It's another important point in triangle geometry in this hyperbolic setting. And it certainly appears as if there's no Euclidean analog of it because, well, the construction here depends very much on this notion of duality to get the points C1, C2, and C3 from B1, B2, and B3. And that duality is absent in Euclidean geometry. So that's the base center theorem. But there's something else that's quite interesting about this base center point B. We'll call it the base orthoaxis theorem. And it says that the base center B that we've just defined of a triangle lies on the orthoaxis A. So here's a triangle A1, A2, A3. Perhaps here is the orthocenter H. Here is this point, the base center that we've just defined, the point B. And here is the orthoaxis of the triangle. Let me remind you what that was. That was the line that goes through the point H and the orthostar S. And what's the orthostar? Well, it's what you get when you take the point H and first of all take its polar with respect to the triangle A1, A2, A3 in the sense of Desargues. That was a line. And we call that line the orthic axis. And that line has a dual point, which is this point S. That's the orthostar. So the orthoaxis of the triangle was defined to be the line between H and S, and now we're claiming that this new point, the base center of the triangle, also lies on this orthoaxis. This is a little bit of evidence to this claim that I made that in fact the orthoaxis is the most important line in triangle geometry in this hyperbolic setting. This might be a good time to say a few words about how to approach theorems in this subject. So 3 steps to understanding theorems. The first step is to try to get a picture of what the theorem says. So we want to draw a picture. And we can do that by hand, or we can do that by a suitable software or program that aids us in visualizing geometry. Geometer's Sketchpad is probably the more familiar of such examples, but there are also other programs that I've also mentioned. CAR, which I think actually should be short for Compass and Ruler. That's a very nice program created by Rene Grothman, and he has distributed this for free. So this is a great program. You can get this for free. You can do geometry, drag things around, make lots of beautiful pictures. That's available online. Also Cinderella, Cabri, GeoGebra, other commercially available programs that do the same kind of thing. But I emphasize that in theory at least, you can do pretty well most of what we're going to be doing by hand, because it all really comes down to just projective constructions, joining points, and taking intersections or meets of lines. You can just use a straight edge to, in principle, illustrate most of the theorems that I'm going to tell you about. Now, when we do that, for example, let's say we're interested in triangle theorem, we should try to have several different pictures. So not just where the 3 points are inside the triangle, but also where some of the points are inside and some are outside, and maybe where all 3 are outside. So we should make sure that we visualize the different possibilities that can arise. Then the second step is to verify the theorem algebraically in special cases. So it means we're going to make computations using the coordinates in special cases. So if you know what the coordinates of these 3 points are, then you can compute the various lines and meets and joins, and you can verify that the theorem actually works computationally. And finally, the third and most sophisticated stage, of course, is to find or to check a general proof. And we're going to see that this is quite a sophisticated undertaking for some of the theorems. Even the 2 theorems that I've already mentioned are reasonably sophisticated. They're not surface theorems. They're a little bit deep. In other words, if you try to find a proof in terms of coordinates, although it's in principle straightforward, you're just doing relatively standard computations with polynomials, it's the complexity and the length of the polynomials that is going to be a challenge for you unless you have a computer helping you. So, following along here, let's have a look at some pictures that illustrate the 2 theorems that I've already told you about related to the base center of a triangle. So here are some pictures that will illustrate the theorems that I've just mentioned. Now let me give you some technology for verifying algebraically theorems, which is sort of the second level of understanding of a theorem. And to make that easier, I'm going to introduce a standard triangle. In fact, this will be our first standard triangle. We might have some more later on. So this is standard triangle number 1. We'll denote that by ST1. It consists of 3 points A1, A2, A3, and explicitly here are the 3 points we're going to consider. A1 is -3 to 3 to 5, A2 is 4 to 0 to 5, and A3 is 2 to minus 4 to 5. And where are these points visually in the plane? Well, here's our standard unit circle, x coordinates, y coordinates. I remind you, to convert a homogeneous coordinate like this, we need to just divide the first two by the third component z. So minus 3/5, that's minus 0.6, 0.6. That's minus 0.6, 0.6. There's the point A1 in our picture. Here, A2, this point here is represented by 4/5, 0, or 0.80. That will be right along the axis there. There's A2. And A3, this point here, 2/5 minus 4/5 is the same as 0.4 and minus 0.8. So that's a little bit like this. And then down there, there's A3. We're going to become familiar with this triangle, and I'm going to compute a lot of things for it. You can check some of these computations yourself, just so then you can make sure you've got the technology right for making computations in the subject, and you'll have a lot of opportunity to compute things on your own for this triangle. So the first thing that we might want to do is to calculate the lines of the triangle. Say L1, which is the line through A2 and A3. How do we compute that? Well, we take a join of these 2 points, A2 and A3. That's the J function. Almost all computations in this subject involve the J function. So we have to take the J of this triple with this triple. And you can check that we get the proportion 10 to minus 5 to 8. And we can check that that's right by checking that this line actually passes through, or is incident, with both A2 and A3. How do we check that? We just compute that 4 times 10 plus 0 times minus 5 minus 5 times 8 is 0. And that 2 times 10 plus 4 times 5 minus 5 times 8 is again 0. In a similar way, you can check that L2, which is this line here, has coordinates 35 to 25 to minus 6. And that L3, this line here, has coordinates 15 to 35 to 12. And I also remind you that these are lines, so they are real lines in the plane. So for example, L3 here, its equation can be read off directly from these coordinates. As a line in xy space, it's the line 15x plus 35y equals 12. And maybe we should also point out that we can take the duals of these lines. So there's L1 there. The dual of that line is just obtained by taking the coordinates, replacing the round bracket with the square bracket. There it is right there. And that's going to be that point L1 there, which in terms of x and y coordinates would be 10 over 8 minus 5 over 8. 10 over 8 minus 5 over 8. There it is there. Similarly for L2, which is going to be off way up there somewhere, and L3, which is going to be up here somewhere. All right, so sticking with this standard triangle, let's compute some altitudes, or altitude lines. Here's our triangle, A1, A2, A3, and we're now going to calculate this altitude line, capital N1. Well, what is N1? Well, it's the line that passes through A1, which is perpendicular to A2, A3. So it means that it's the join of A1 with the dual of A2, A3. Well, the dual of A2, A3, that's the point that we called little l1. So we have to take the join of A1 with L1. And that's again a computation with the J function. And you get 49 to 74 to 15. So the equation of that altitude is 49x plus 74y equals 15. And similarly, you can check that N2, this altitude here, is 125 to minus 199 to 100. And N3, this altitude here, is 223 to minus 51 to 130. And now we can calculate the orthocenter, which is the meet of these three altitudes. Because we can calculate the meet of any two of them. either N1, N2, N2, N3, or N3, N1. We'll get the same result no matter what we do. And here, in fact, is the result of that computation. So you can take the join of this one and this one, or this one and this one, or this one and this one. And after you divide by a common factor, because I always get rid of the common factors, okay, you can end up with this point. 10,385 to minus 3,025 to 19,001. This little green underline here means that this is actually a prime number. Okay, I'm kind of interested in primes. If there's a prime floating around by itself, I might underline it in green. That's the orthocenter of the triangle A1, A2, A3. That's the coordinates of that point H there. And now we can calculate the base points as well. The base points are these points B1, B2, B3. So for example, B1 is the meet of N1 with L1. N1 with L1. There's N1, L1 on the previous slide. Another join operation. You get this one here. 667 to minus 242 to 985. B2 is 653 to minus 2,125 to 5,045. And B3, 2,581 to 363 to 4,285. See, we're getting very explicit answers. This should make us feel good. It's very computationally explicit, this theory. But that's not all we can do, said the cat in the hat. So here's our triangle again. A1, A2, A3. Our base points B1, B2, and B3. And now I've joined those base points with lines. Those three lines form the orthic lines. Those 3 points, B1, B2, and B3, that's the orthic triangle. So how do we get the equations of these orthic lines? Well, they're just joins of the 2 base points involved. Those are the B's that we've just found, so we can find the joins of them. Here they are here. There's C1, C2, and C3. Now the duals of those lines, the dual of this line that's C2 will be that point C2 there. The dual of this line C3 will be this point little c3 down here. And there's C1, that line, its dual down here. So one of the uses of these orthic lines is it determines the orthic axis. This is the polar of the orthocenter with respect to the Desargues polarity of the triangle, A1, A2, A3. So how does that go? Well, I remind you that if you take these 2 points here and you intersect where it meets this line here, that's one of the 3 points that lie on a line. The other one is obtained by taking this line here and seeing where it meets this line. There's another one. And then this line where it meets this one is another one. And Desargues' theorem tells us that those 3 points are collinear, and we call that the orthic axis, and denoted by S. Okay, so now it's a bit of a computation. You can compute what this line is by computing 2 of these 3 points and finding the join. So how would you compute that point? Well, you would take that line and find the meet of those 2 lines, etc. So you can check that this orthic axis has coordinates 7290 to minus 415 to 7,889. And then its dual point is what we call the orthostar of the triangle. Little s, there it is right there. The dual of the orthic axis. And that point S, together with the orthocenter H, forms our orthoaxis capital A. So we have a formula for the orthocenter. We have a formula for the orthostar. It's just the dual of this line here. So we can use the J function to find the join of those 2 points. And here it is right here. So the orthoaxis of this triangle is 187,986 to minus 665,765 to 2008,735. And something else that we can do is we can find the base center. Well, how do we do that? There's the base center there. It's where this point and this point, it's one line, meet the join of this point and A3, which is there. And also where A2 and C2 meet. It's the common center of perspectivity between A1, A2, and A3, and C1, C2, and C3. And there it is right there. And you can calculate that is this. And so now we're in a position to directly check what we call the base orthoaxis theorem. The fact that the base center B lies on the orthoaxis A. That's the computation that this number times this number plus this number times this number minus this number times this number is 0. You can see that it's somewhat non-trivial, even with this relatively simple triangle that we started off with. So a great exercise if you're numerically inclined. Try to check some of these things. Maybe you can make some other computations relating to this interesting triangle. Here now is another interesting theorem that in fact sort of connects this base center with some Euclidean triangle geometry. Let's call it the base triple orthocenter theorem. What does it say? Suppose that the triangle A1, A2, A3, and we're talking about a general triangle now, has orthic triangle B1, B2, B3. I remind you that that means that B1, B2, and B3 are the bases of the altitudes of this triangle. Suppose that H1, H2, and H3 are the respective orthocenters of these three triangles. The triangle A1, B2, B3, the triangle A2, B1, B3, and the triangle A3, B1, B2. Then, first of all, the orthocenter of this triangle of orthocenters, H1, H2, H3, is the base center B of the triangle A1, A2, A3. That base center that we've just been talking about. And furthermore, this base center B is actually the center of perspectivity between the original triangle, A1, A2, A3, and this triangle of orthocenters, H1, H2, H3. So these two triangles are in fact perspective from a point, and that point is exactly the base center B of the original triangle. Let's have a look to see what it looks like picture-wise and algebraically. So in our standard triangle number 1, there it is there, A1, A2, A3, with our base points B1, B2, and B3, and the base center B right there. What we're talking about here is three other triangles. First of all, the triangle A1, B2, B3, the triangle formed by those 3 points. It has orthocenter, which happens to be H1 right there. Then the triangle A2, B1, B3, this triangle right here, it has orthocenter, which is that point right there, which is H2. And the triangle A3, B2, B1, that triangle right there, it has orthocenter H3, which is right there. And so that base triple orthocenter theorem that we just mentioned tells us two things. That first of all, these three orthocenters, H1, H2, H3, they form a little triangle whose orthocenter is the base center B of the original triangle. And furthermore, this is actually the center of perspectivity between this triangle, H1, H2, H3, and the original triangle, A1, A2, A3. So that these lines emanating from B up here, which are already lines that we've seen before in a previous diagram, also are the lines on which H1, H2, and H3 appear. How about algebraically? Suppose we want to check using actually our standard triangle number 1, the actual coordinates that we've been using. Okay, well, We know what all the coordinates of these various points are. With some labor, we can calculate what the orthocenters of these three triangles are. And I've done it here for you. Although if you like, you can easily check, or maybe not so easily, but you can check that these calculations are correct. So H1, this point right here, is the point. Well, there it is there. That's its first coordinate, that's its second coordinate, that's its third coordinate. That third coordinate happens to be prime. H2, the orthocenter right there, that happens to be this point. There's first coordinate, second coordinate, third coordinate, also prime. And H3, which is right here, that's that to that to that. So if we took those 3 points and we calculated the orthocenter of that triangle, we would end up back with the base point B that we calculated earlier. So it's non-trivial. Okay, we are in a situation where the theorems are perhaps reasonably easy to find, especially with Geometer's Sketchpad or some equivalent program, and maybe not too hard to verify in special cases like this one, but to actually prove them algebraically or synthetically will require some application, some skill, and maybe just some raw computing power. It turns out that the range of theorems relating to perpendicularity is expanded considerably once we include the points that we've not been paying too much attention to up till now. The null points and their duals, the null lines. These are central objects in hyperbolic geometry, and next time we are going to start focusing on them. And we'll see that when we do, a whole new range of interesting theorems comes into focus for us. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.